In this presentation, I'll be explaining the effect of source impedance on the performance of three-phase full-wave converter. Now let us see the effect of source impedance on the performance of converters. And here we are considering a three-phase converter, full-wave converter. And in the previous presentation, I have considered for a single-phase full-wave converter. Here, three-phase full-wave converter is being considered. And here the source has an inductance and a resistance. The source is by having, if it is having an inductance as well as resistance, or that impedance is there. Now one thing is that, for example, here first we'll assume that if there is no inductance and resistance of that, if there's no inductance, we can say that one, that already we have explained that without inductance, that presentation, the previous presentation. And here if there is no inductance, we can say that there is a the firing sequence will become first T1, then next T2, T3, T4, T5, T6, like that one, and each device will be conducting for 120-degree duration. And as we see that the device conduction period has been marked like this one. For example, before T1 is fired, T5 was for conducting from the positive group. This is a positive group of SCR and this is a negative group of SCR. At any instant in that case, one from the positive group and one from the negative group will be conducting. As an example, before T1 is conducting, T5 will be from the positive group and T6 from the negative group will be conducting. And at this instant, T1 is being fired. Then T1 is the incoming SCR and T2 is the outgoing SCR. And from the positive group, the current will be transferring from T5 to T1 instantaneously it is changing, and then it will become T1 and T6 will be conducting. Like that it continues. That is, if there is no inductance for the source side. But if there is an inductance on the source side, that is the current through the incoming and outgoing SCR does not change instantaneously due to the source inductance. In that case, if you the same thing, if you consider here, for example here, then when you are giving, say, first T5 and T6 are conducting, assume that one. Now we are firing the T1 when it is positive bias, or when it is getting forward bias, like that one, that is being triggered. But in that case, when T1 is triggered here, that is the incoming SCR, but the outgoing SCR T5 it has to go switch off. But that does not go instantaneously. In that case, what happens is that from the positive group, both T1 and T5 conducts. From the positive group, both T1 and T5 conducts, and from the negative group, T6 is conducting. That is like this one. And then after some time, the current through this T5 is decaying to 0, and here the current through the T1 is increasing to the this current, the load current, the I0. Therefore that happens after this one. Same thing after sometimes after 60 degree T2 is fired. Then after then T2 is fired means in that case here, here again this region, in that case T1 is firing from the conducting from and from the positive group, and T2 and T6 are conducting. That is here T2 and T6 from the from the negative group are conducting. In that one here T2 the current is building up and T6 is current is decaying. Therefore during that period, again the load current here through T1 the I0 is conducting, and through this one I0 is firing, and here one is current is decaying, another one is current is here decaying, and here current is building up. Therefore that happens because the source inductance, that period during which it is both SCR in the same either positive or negative groups are conducting, that is called the, of course, the overlap angle. That's called the that is a mu, it is a conduction angle, is the mu angle, that is that is mu. And because of this one, there will be a reduction in the output voltage, just like a full wave converter. Now that is the one effect due to the source inductance at the inductance at the source side. That's a phase. This is a three-phase full wave converter. Now another thing is that because of the resistance, there will be a voltage drop at the source, because if there is a resistance at the RS is here, because of this load current I0, that I0 into RS in this phase be dropped. That one here total drop will be in a three phase, it will become 2 times I0 RS will be dropped, so that the voltage at the input of this one the converter reduces, and again the output voltage reduces. Therefore there will be a reduction in the voltage at the input of the converter because of the source resistance, and similarly source inductance. That is, we'll be seeing in the next slides the derivation of that, how much voltage is being dropped as such. Therefore, for a three-phase case, for a three-phase case, the output voltage equal to 3 root 3 Vm by pi cos alpha if the commutation, I mean I mean overlap angle equal to 0, it is mu equal to 0. That's it. If the inductance effect is neglected, it is the equation. But if you are considering the source inductance as well as source resistance, the output voltage equal to, there will be drop of 2 I naught Rs, where Rs is the source resistance, and 3 omega Ls divided by pi into I naught. This is the drop due to the source inductance. Therefore, this is the output voltage equation for the three-phase, I mean, three-phase full wave converter, considering the source resistance as source and source inductance. We'll be deriving the equation in the next slides. Now let us see the of source inductance on the performance of three-phase full converter. This is the circuit topology, and this is the load. And here, this is a positive group of SCR. This is called the negative group of SCR. T1, T2, T3, T4, T5, T6. The firing sequence is normally T1, T2, T3, T4, T5, T6, again T1, like that one. And this is the source inductance. In this one, we are when we are neglecting the drop in the source resistance, normally we are considering only the source inductance. Therefore, Ls is the source inductance, and the three-phase supply input is given here. Ls is the source inductance in each line, and load current is assumed to be, but we are assuming the load current is constant. Current through the load is constant. Now, first assume that just firing angle equal to 0. Assume that firing angle equals 0 here, because alpha, we are taking alpha equals 0. Here, it is fired. For at this instant, the T1 is fired, like that one. Here it is fired. T1 is fired at this instant. And here, before that, T5 was at this instant, T1 is fired. T5 also is there. Therefore, T1 is fired. Previously, T5 was conducting. Therefore, because of the inductance of the source side, T1 is the incoming SCR and T5 is the outgoing SCR. But normally, if source inductance is not there, T1 current through the T1 suddenly increases instantaneously and T5 reduces to 0. That is, but in this case, the current through T1 is slowly increasing, that is rising slowly, and the current through T5 is decaying slowly. Or during that, this is the overlap period. This is overlap angle mu. This one overlap angle. The same time, from the negative group, the T6 is conducting. Therefore, T1 and T5 are from the positive group, and T6 from the negative group of SCR conducting during this overlap period. Therefore, that is the current changes during like this one during the overlap. Therefore, first assume that firing angle equals 0 and overlap angle mu is equal to. First, we are assuming the overlap. In this case, overlap angle equals 0 here. In this case, as we have already explained the previous presentation, here if this inductance is 0, here it is like that T1, T2, T3, T4, T5, T6, T1, like that. That's fired, and each one device will be conducting for the 120-degree duration. At any instant, only two devices will be conducting, one from the positive group and one from the negative group. That is happening if the source inductance is equal to 0. That is, mu, the overlap angle equal to 0. But if source inductance is not 0, there will be overlap angle comes here. That is why always two from one group and one from the another group, second group, will be conducting. As an example here, T1 and T5 are conducting from the positive group, T6 from the negative group. And here T2 and T6 from the negative group, and here T1 from the positive group. So these are the shape of the current. Here it is marked as current IA and IC. The current through the phase A and the current through the phase C are marked at this one. That is, the current is building up like this one. For firing sequence 0 is pure. Conducting SCR is, that is, if mu equal to 0, these are the conducting SCRs. And it is marked here what are the devices that are conducting if the overlap angle equals 0. Now we will see next one, considering the effect of source inductance. Then what are the devices that are conducting? Now continuing the effect of source inductance on a three-phase full wave converter, in which we can see that T1, T3, T5 positive group of SCR, T2, T4, T6 negative group of SCR. These are the source inductance. Three-phase supply is given. This is a RL load, which makes the load current constant. And now the firing angle is 0 and the overlap angle. Now next case what we are considering is the firing angle equal to 0, but there's an overlap angle mu here it is. Therefore, due to the source inductance, that is here, the outgoing SCR current decays. That is, as an example, I told you, that T1 is fired, but that is the incoming SCR. T5 is the outgoing SCR. Therefore, T1 and T5 will be conducting the same time, and from the positive group. T6 will be from the negative group. That happens here. Therefore, outgoing SCR current decays slowly and the incoming SCR current builds up slowly. Example T5 and T1. Here we can see that here the T5 current is increasing slowly, and similarly here other current is decaying. That is, T5 current is slowly decaying and T1 current is slowly building up. And during this period, the two from the one group and one from the others group will come. During this period, here T1 and T6 will be, T1 and T5 will be conducting from the positive group, and T6 will be conducting from the negative group. T1, here example, T5 and T1 will be from the positive group, and T6 from the negative group will be conducting. And the shaded portion represents this overlap period. That is, this portion will be representing the overlap angle mu here. That is because of the source inductance. These are the phase voltages VA, VB, VC, and the output voltage, that is the voltage at this point as well as the voltage at this point. The difference of that voltage is the output voltage. Now, if you see the voltage at this point, at the positive terminal, it is marked like this one. It is marked like this one. And the voltage at this point is that is lower one is the voltage at this point. So difference of that one is whatever this shown here, the difference is that is voltage coming across the load. And in this case, if you see, we have to derive what is the voltage when two phases are conducting from the one group. Then we'll be deriving the equation for reduction voltage. Because of the two phases are conducting, what happens is that this triangle, that much voltage is being reduced, or how much the voltage is reduced because of the inductance at the source side, we'll be deriving in the next presentation. Now there are the cases, as I told you, when T1 is fired, T5, which was already conducting, that has not yet turned off. Therefore, both, that's called outgoing SCR. This is the incoming SCR. Therefore, both T1 and T5 will be conducting from the positive group, and T6 will be conducting from the negative group. Therefore, that equivalent circuit is like this one. That is, because of T1 is conducting, that inductance comes, source inductance comes here. And here, the next one, here T5 is conducting. Therefore, the phase C also coming here. And then that's coming to the load, and through the negative side, T6 is conducting. That is coming to the returning back to the, this is coming back to the phase B. Therefore, this is the equivalent circuit of this three-phase full wave converter, considering the source inductance. For the case at which both T1 and T5 are from the positive group conducting and T6 from the negative group conducting. That is because of the source inductance. Two from one group and one from the other group will be conducting. Therefore, in order to solve this one, during the overlap period, that is the overlap period means here overlap period, this one, these are the overlap period. That is both T1 and T2 will be conducting. That during that overlap period or the overlap angle mu, what here is IA plus IC, that is the current through the phase A and through the, for in this case, both are conducting. IA plus IC will be constant, that is equal to constant load current I0. And of course, through this one, the return capital I node is flowing to the phase B. Therefore, here, if you coming first will be this is the condition. First, we will be deriving applying the Kirchhoff's voltage law to this. Then what we'll be getting is VA is applying that VA minus, that is the potential rise. There is a potential drop LA DIA by dt, that is coming here. That is minus, of course, here this drop across this one V0, that drop across minus V0. Then drop across, this is minus 2, that's potential rise. That is why LS dIB by dt, again it is this minus plus potential, this plus and minus here. Therefore, it is equal to potential drop, which is minus VB equal to 0. That's equation 0. That is, this loop is KVL applied to this loop. Then second, same thing KVL is applied to the second loop here. That is equal to here VC comes here. VC minus this drop, that is LC DIC by dt, then here drop minus V0, then this one, so potential right, plus LB DIB by dt, drop across this inductance in phase B, then again minus VB equal to 0. Therefore, that is the second equation, this applying the KVL to this loop. Therefore, from these two loops, and one more thing is that as I told you, IA plus IC equal to a constant, and DIA by DIA by DT plus DIB by DIC by DT equal to 0, or DIA by DT is equal to minus DIC by DT. That is, these are the two SCR from the positive group conducts, and this is a negative group conduct. Therefore, here the current is building up, here the current is decaying, but the sum of this current will be constant I naught. And if you differentiate DIA by DT plus DIC by DT equal to 0, or DIA by DT equal to minus DIC by DT, and here substituting this one here in this equation here, we can see that BC substituting this one here, BC plus the LS DIA by dt minus V0 plus LS DIB by dt minus VB equal to 0. Substituting this one here. Therefore, then what we are doing that 1 plus 4 is that this equation first and 4 are added, and then we'll be getting the final adding equation 1 and 4 in getting as VA plus VC minus 2V V0 minus 2 LS DIB by dt minus 2 VB equal to 0. Or here DIB by, because the current through IB is constant, this load current is flowing constant, because only the current is increasing here, decaying here, but the current through this during that period, this is a constant I naught. Therefore, DIB by DIB by DIT equal to 0. DIB by DIT equal to 0. Therefore, substituting that one here, since IB is constant, then from this equation we'll be getting what is output voltage is equal to during the overlap period. That is, during this overlap duration, the output voltage equal to VA plus VC, the phase voltage of A plus the phase voltage of C divided by 2, that is that minus VB. This is the voltage during this overlap period. Therefore, that is the equation for the output voltage during the overlap period. Now you have to calculate how much voltage is dropping by because of the cell inductance at the source side. That's source side inductance. What is the drop here? That is this triangle. You have to calculate this area of this triangle. That is, then we have to subtract that one. To calculate this area of this triangle, we can say that one average value of the falling output voltage due to the overlap. That is because of this area. This area, that is the falling voltage because of the source inductance, equal to the triangle area JKL. That is this triangle area JKL divided by the periodicity of this triangle, which is equal to pi by 3. Pi by 3 means it's equal to pi by 3 here. And that is 180 by 3 or 60 degree interval. This period, this will be coming in this interval. That is why, in order to calculate how much voltage is reducing this one, it is calculated. It is the area of the triangle JKL divided by the periodicity. Therefore, 1 by pi by 3 integral 0 to this one. Actually, this is the conduction in this angle, that is mu. It is the overlap angle mu. Therefore, it is overlap angle. Sorry, it's overlap angle 0 to mu integral BL d omega t. For this, therefore, that is equal to 3 by pi integral 0 to mu, and here LS di by dt d omega t. Or the reduction in voltage is equal to 3 by pi. 3 LS is taken outside. 3 LS divided by pi integral 0 to, in terms of omega, will be taking 0 to mu by omega di by dt into dt, or 3 by ls by 3 omega ls divided by pi into 0 to I naught. That is, during that period the current is changing from 0 to I naught into dt, or that is equal to, if you take 3 omega ls I naught divided by pi, 3 omega ls divided by I naught pi is this area over one cycle. There are such, there are pi by 3 interval that is there. This much loss, this much reduction in voltage is there. That is calculated. Therefore, that is equal to 3 omega ls I naught divided by pi. That is why if the source inductance is not considered, the corresponding average output voltage equal to 3 VML by pi cos alpha, or in terms of phase angle, phase voltage 3 root 3 Vm by pi cos alpha. This is the line voltage. 3 VML by pi cos alpha is the average voltage if overlap angle mu equal to 0 or source inductance equal to 0. There's no overlap. But once this, this overlap angle, that is mu, comes here because of the source inductance, there will be a reduction in voltage, and the reduction in voltage is because that is why here we are considering this area of this triangle, and that is calculated as 3 omega ls I naught divided by pi. Therefore, that reduction voltage is this much. Therefore, the output voltage with overlap mu equal to 3 VML by pi cos alpha minus 3 omega ls divided by pi into I naught. Therefore, I naught is the load current, constant load current, and ls is the source inductance, and of course alpha is the firing angle. Therefore, the average output voltage across the load in a three-phase full wave converter, considering the source inductance Ls, given by 3 VML by pi cos alpha minus 3 omega Ls divided by pi into I naught. Therefore, there will be a reduction in voltage. To this portion is the how much is voltage is being reduced. As the load current increases, there will be a reduction in voltage. This much 3 omega Ls divided by pi into I naught. That is because of the source inductance. And output voltage for a three-phase full wave converter similar to that is given for a single-phase full wave converter. As single phase similar to that one, again you can derive it as one more equation is that in terms of alpha plus mu, similar to the single phase, V naught equal to 3 Vm pi cos alpha plus mu plus 3 omega Ls divided by pi into I naught. This one more equation is the similar to the single phase full wave converter. This in terms of alpha and the mu, that is overlap angle. V naught equal to 3 VML by pi cos alpha plus mu plus 3 omega Ls divided by pi into I naught. Therefore, this is the equation to calculate the output voltage as low as we consider the source inductance Ls. How much voltage is being dropped here? That is this one. And as the load current increases, that voltage drop will be more. And just like it's like a voltage regulation happens. As the load current increases, there will be a drop in voltage. Now let us see a problem on this three-phase full converter bridge, which is connected to a supply voltage of 230 volt per phase, 50 hertz. The source inductance is 4 millihenry. The load current on the DC side is constant 20 amperes, current constant 20 amperes. If the load consists of a DC voltage source of 400 volts having an internal resistance of 1 ohm, then calculate the firing angle and the overlap angle. And if the if the load consists of a DC voltage source of 400 volts having an internal resistance of 1 ohm, that is here it is a battery or DC source with a internal resistance of 1 ohm. That is, it is actually charging the battery like that. The load can be considered as a battery charging having a 400 voltage as well as an internal resistance of 1 ohm. Therefore, this is the source resistance. Therefore, this is a circuit topology. Let us see that one. We are asked to finding out what is the firing angle and what is the overlap angle, alpha and mu. Now coming to the load current is given as 20 amperes. And internal resistance is given as 1 ohm of this. Internal resistance of the battery which is here is equal to 1 ohm. Therefore, the DC voltage equal to that is given here as 400 volts. Therefore, the converter output voltage is given by, if you see the voltage here is equal to the battery voltage plus the drop across the internal resistance. Therefore, it is equal to 400 volt plus what is the drop in the internal resistance? 400 plus 20 into 1 ohm, or 420 volt is the voltage. For the voltage to be across this battery, it should be equal to 420. 420 volts is that. Now the output voltage with overlap, if that is if considering the source inductance, the equation for the output voltage is given by 3 VML by pi cos alpha minus 3 omega Ls divided by pi into I naught. And here I naught equal to 20 amperes. And you can substitute in the equation output voltage with overlap. You need 420 volt here. You need a 420 volt at the output. Therefore, that we are 420. 3 into root 3. That is in terms of line phase voltage. Calculating. That is why it is root 3. I have multiplied like that one. 3 root 3 into Vm phase voltage maximum value. Root 2 into RMS value of the phase voltage. Root 2 into 230 is the maximum value of the phase voltage into root 3. Maximum value of the line voltage into 3 or 3 VML divided by pi into cos alpha minus 3 into omega 2 pi into f equal to 50 into inductance equal to 4 into 10 raised to minus 3 divided by pi into I naught equal to 20 amperes. Therefore, substituting here from this equation, you can derive what is the cos alpha equal to 0.8253 or alpha equal to 34.382 degrees. For the firing angle of this thyristor is calculated as 34.382 degrees, corresponding to this condition to have a voltage of 420 volt here. And the output voltage can be expressed as, again, one more equation is there. We are saying output voltage equal to 3 VML by pi into cos alpha plus mu plus 3 omega ls divided by pi into I naught. One more equation to in terms of overlap angle mu. This is another equation to same output voltage 420. Again, you substitute in this equation 420 equal to 3 VML, that is 3 root 3 into root 2 into 230 divided by cos alpha plus mu plus 3 2 pi f into L ls, that is the source inductance 4 millihenry, 4 into 10 raised to minus 3 divided by pi into 20, and alpha is already calculated 34.382. Therefore, from this equation you can calculate what is alpha plus mu, and which is equal to 0.73, cos alpha plus mu equal to 0.736, or alpha plus mu equal to 42.602 degrees. Or from this one you can calculate mu equal to this one minus alpha, that is 42.62 degree minus 34.382 degrees, which is equal to 8.22. Therefore, the overlap angle mu equal to 8.22 degrees. Let us see one more problem here. A three-phase fully controlled bridge converter is connected to 415 volt, that is a line voltage supply. That supply has a reactance of, not inductive, reactance has been given 0.3 ohms per phase and resistance 0.05 ohms per phase, and the converter is working in an inversion mode, that is power is flowing from the load side to the source side. As an inverter, it is the firing angle should be more than 90 degree. The firing advanced by 35 degree. Actually, firing advanced by 35 degree means that the firing angle is equal to 180 minus 35. Therefore, alpha will become 180 minus 35. Compute the average generator voltage. Therefore, here actually this is a generator voltage to calculate, because power is flowing in the reverse direction. And what is the average generator voltage is? Assume that load current equal to 60 amperes and thyristor drop is equal to, that is also given as 1.5 volt per thyristor. 1.5 volt drop is. In a three-phase full converter, the voltage drop due to the source resistance, in a three-phase it is the drop due to the source resistance equal to 2 I naught into Rs. 2 I naught into Rs is the total drop resistance drop comes here. And voltage drop due to the thyristor drop is equal to 2 times Vt. 2 times Vt is that. But the voltage drop due to the inductance equal to 3 omega ls divided by pi into I naught. These are the voltage drop due to resistance, inductance, and the thyristor. All these drop we have to subtract from this one. Therefore, available voltage at the output side of the here, this voltage is equal to 3 VML by pi cos alpha minus the drop, the resistance 2 I naught Rs minus the drop in the thyristor 2 Vt minus the drop due to the inductance, source inductance. That is the output voltage. Since the converter is working in an inverter mode, of course I told you, it's inverter mode, the firing angle will be more than 90, and advance angle is given as, say, it is advance angle is 35. Therefore, firing angle will be 180 minus 35. Therefore, in this equation here, of course, this is the 3 VML by pi cos alpha. This is the drop due to the resistance of the source, and this is the drop due to the inductance, or actually reactance of the source, and this is the drop in the thyristors. Therefore, if you subtract this one, only if this is more just above this is a voltage. If this voltage should be just above this one, then only there will be a current in the direction. Therefore, the average generator voltage, therefore here E should be equal to the back EMF, just like a back EMF. That should be equal to, then only the power will be flowing here. So it's working that here 3 into, from this equation you can calculate 3 into 415 divided by pi into cos 180 minus 35 minus 2 into 80 into 0.04 minus 2 into the drop in the thyristors minus 3 omega ls, that is rather than omega ls, it is reactance is given. Source reactance 0.25 ohms, 3 into 0.25 divided by pi into 80, or 487.522 volts. So that is the source voltage, or the generating voltage, not source voltage. Generating voltage, that is E. That much average generator voltage should be equal to this much, 487.522 volts.